Welcome to Chem Help ASAP. In this video, we will isolate aspirin, O-acetylsalicylic acid, from aspirin tablets. This is a classic experiment that students do in either high school or college. We will do this experiment with a more college-level view of the process and discussion of how the properties of aspirin affect the isolation process. The video description contains links to supporting documents, including the laboratory procedure and proton NMR spectra. A very common type of experiment you'll perform is the isolation of a material from some mixture. So you want a pure material, but the material is currently found in a mixture. So a classic example of this is something like what we're going to do in this video. We're going to isolate aspirin, and the structure of aspirin is on the right. Sometimes this is called acetylsalicylic acid or ASA. And we're going to isolate this from tablets. These are aspirin tablets. And so this is one type of isolation. Now in this case, the tablets represent the drug product. This is what the consumer receives for the medication. So the drug product contains a lot of different things. It contains different binders, which give the pill its shape. It can contain dyes. It might contain some salts. But what it also contains is the drug substance. And in this case, aspirin is the drug substance. Often people refer to the drug substance as the active pharmaceutical ingredient, or the API. So that's what we're going to do in this video. We're going to isolate the API of aspirin, which is acetylsalicylic aspirin, from the drug product, which includes not just the API, but also binders, dyes, and salts. This doesn't have to be done with tablets. People do product isolations from all sorts of things. People take leaves from the coca plant and they isolate cocaine. So you can take natural substances, leaves and plant material, even animal material, and extract out pure ingredients. But for this experiment, we're going to look at aspirin pills and getting out aspirin itself. Alright, so here is the same slide again. We just cleared the screen. How is this going to work? Well, we're going to take 30 aspirin pills. So it's nice to work with a fair amount of material, and to get a fair amount of material, we're going to use quite a number of pills. So we're going to take 30 different aspirin pills. We are going to mechanically grind them up. We're going to basically turn them into a powder, and then that'll increase the surface area of these pills, and that will allow us to extract the aspirin out of this pill material. So what we're going to do is a solid liquid extraction. The aspirin will go into our liquid, and left behind will be a solid residue, and that solid residue will be the starches and binders that make up the pill. And once we get our aspirin into a liquid layer, then we'll need to precipitate out our desired aspirin in some form. So that's what we're going to see in this procedure. We'll take some pills, grind them up, and then hopefully extract out the aspirin. Okay, we're at the balance and we're ready to start this experiment. So what we have are some tablets. These are aspirin tablets. Each tablet contains about 325 milligrams of the active ingredient, which is aspirin. So for the procedure, we need 30 tablets, and in this small 50 milliliter beaker are 30 tablets. The balance is already tiered for the weight of this beaker. So when I put this on the balance, we get a mass of 11.31 grams. So 11.31 grams, if you take 325 milligrams and multiply it by 30, you get just under 10 grams. So I'm weighing just over 11 grams. So there's maybe 1.5 grams of extra material in these tablets, which is not aspirin. So our goal for the experiment is to separate the non-aspirin stuff from the aspirin itself. So we're going to have to grind these up and do a solid liquid extraction. So we have our material, we have the mass of the material, and now we will go to the hood and commence this extraction process. Okay, let's get started. This is our beaker with 30 aspirin tablets, and we kind of have the star of the show. This is a mortar and pestle. The mortar is this ceramic bowl, and the pestle is what we're going to use to grind up these tablets. Mortar and pestles, because I'm a chemist, I associate these with chemistry labs, but the fact is you encounter them in cooking, you certainly encounter them in drug formulation. So we're going to take our 30 tablets, put them in here, and the first course of action is to try to just kind of mush up these big tablets, because really big things are hard to grind up. So first, I'll just directly kind of smush each tablet. And here's kind of what we're looking at. You can see some of those tablets are broken up a bit, and some are pretty intact. So we're going to try to make sure we roughly get everything into smaller pieces, and that way when we grind... Okay, that's pretty good. Okay, so that's kind of powdery now, but we can do a whole lot better than that. So now, I hope this isn't too loud on the microphone. This grinding noise is not the most pleasant. I never want to grind this stuff long enough. I always want to declare it done too early. You can go a little bit extra and try to get this as a pretty fine powder. And that's pretty decent. Okay, so as you can see, it takes very little time to crush up these pills. These pills are, they're not made out of rocks. They're made to break down in the body. So they actually come apart pretty easily. So now we have a funnel on a flask. This funnel, this is a powder funnel. So powder funnels tend to have kind of a fat stem, or I'm sorry, kind of a wide opening in the stem, and kind of a short stem as well. And that minimizes the chance you're going to plug up your funnel. So there are different types of funnels for different uses in a lab. So let's take our solid, and now we're going to try to get this in the funnel. It's a little bit delicate. This mortar actually is pretty heavy. I mean, it's not going to strain your back, but it's got a little heft to it. These things they're made to do some work. Okay, we'll just get the best we can. That's actually pretty good. Maybe better than I expected. And now I'll use this micro spatula to sort of scrape some of this off. And again, our goal is not to get this pristine and clean. We just want to get the vast majority of this solid out of here. Okay, that's better. Now the old tap, 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 tap. We lost a little bit there, but not too bad. Okay, wonderful. So we still have this solid here, and I definitely want that solid. It doesn't represent a large percentage of our mass, but it still does represent some. So what we're going to do is we are going to extract this powder with isopropanol. So instead of just dumping isopropanol into the flask, we'll use some of this isopropanol to try to rinse out our mortar. So this is about 50 milliliters. This is what the procedure calls for. Let's pour just a little bit of this in here. I'll do a little more than that. It's maybe 20 or 20. Whoa, that would have been a disaster. 20 or 25 milliliters. Swirl this around. That looks pretty good. And now we'll dump this through. Maybe make sure all the powder gets rinsed down too. That's pretty nice. Add the rest.
swirl this around, hold it high enough so we don't dump over our flask again. Okay, clearly not perfect, but pretty good, and the point is it's much better than it was. Now you can't see how much powder's left behind because we got it all wet and it sort of fades into the background, but whatever is left in there is certainly less than when we first started the rinse. Okay, so now we are ready to go ahead and extract this. So we have isopropanol, we have the solids from the pill. Those solids include aspirin, as well as things like the binders that are found in these tablets. So we're going to extract this. Presumably our aspirin is going to go into the isopropanol layer, and some of these solids, these salts and binders, are going to remain as solids. So even though we've done the extraction, we're still going to have solid in the bottom. That doesn't mean it's failed, that just means we've extracted what we want. So I need to do two things. One, I'm going to put a stir bar in here, and two, I'm going to put this on a stir plate and just let it stir gently for about 30 minutes. Okay, this has been stirring now for about 30 minutes. Note that it is only stirring. The stirrer is on. We don't have any heat. And presumably what we've done is we've extracted all the aspirin out of that solid material and into the isopropanol. Note there is a stir bar in there and we are agitating the solution. So let's go ahead and take this off of the stir plate. And now we're going to filter these solids. And we expect to see solids because that's the residue left from these tablets. So we're going to filter this into an Erlenmeyer flask. We're going to use a filter paper that's been folded to fit into the funnel. And for this funnel, note that we have a long, narrow stem. This is a liquid funnel where we have with the long stem. And we can do this filtration. Now isopropanol is a pretty thick solvent, pretty viscous solvent, so this is not going to filter in just 2 seconds. Great. Okay, we are dripping through. Now, we are doing a gravity filtration. This is not a suction filtration. When you typically do a gravity filtration, that is a sign that you want to remove the solids and you actually care about the liquids. Normally, suction filtrations are when you want to collect the solid and the liquid might be waste. So in this case, we want the liquid, so we're just doing a gravity filtration through this filter paper. And of course, under certain circumstances, that logic may vary, but in general, gravity filtrations are when you don't care about the solid, but you want to collect the liquid. So we're going to let this drip, and this is going to take a few minutes, so we don't have to show all of this, but we'll wait till this is fully dripped through, and then we'll talk about what we're going to do about this residual solid and any residual product that might be in here, and stuff that might be caught in the funnel. Well, this has finally dripped down a whole bunch. It's essentially all the liquid has come through the funnel. Now we have these solids to deal with. Now these solids, we want them to be solids, but presumably there could be some products sticking to these solids, as well as the solids that we've collected in the funnel. So I'm going to use a small amount of isopropanol to rinse all this down. Now we don't want to use a lot of isopropanol, because the next step is we're going to mix this isopropanol solution, which contains our product. We're going to mix this with water, and our product is going to precipitate out. But if we use a whole bunch of isopropanol to rinse everything out, get everything spick and span and clean, then we're probably not going to get as good a precipitation when we add the water. So we need to very judiciously use our isopropanol. And what that means is we might actually not get a 100% rinse here because we don't want to add too much isopropanol. I've got about 10 or 15 milliliters here. So the thing is, we know our product is soluble in isopropanol. So the more isopropanol we use here, perhaps the less precipitation we'll get when we add water. Now we could just try to add more and more water, but then you're just starting to make a mess. You're just using tons of solvents as a guessing game. So let's try to minimize our use of isopropanol right here. And I'm just dripping isopropanol down this funnel so that it flows through the paper and hopefully rinses off any aspirin that is trapped in that filter paper. And I think I'm going to stop there. Am I stopping because I know that the rinse is complete? No, I'm not. I'm stopping because I feel like I've done a little bit of rinse and the bulk of any left behind material has now been collected. And if we miss a little bit, that's fine, because hopefully we'll recover even more because we use less isopropanol in this stage. So I'm not doing this with certainty. I'm just making my best guess. It's good enough to carry us on. So we'll let this drip through and then we'll tackle our precipitation step. So fantastic. So this has all filtered through. We have residual solid in there. This is presumably waste. We won't throw it out until we get our actual material isolated. But here is our aspirin dissolved in isopropanol and separated from the other salts and binders that you find in the pills. So now we need to get this material. We need to recover our aspirin from the isopropanol. So what we have in this larger flask is about 250 milliliters of water. Now I've done this experiment in the past, and what I found is that aspirin has low water solubility if the aspirin is in its neutral protonated form, its carboxylic acid form. And so not only is this about 250 milliliters of water, but it's about 1% sulfuric acid. Now 1% sulfuric acid is plenty acidic. It has a nice low pH, so that will make sure that we have our protonated form of our carboxylic acid. Now this isn't just concentrated, so you think, oh, a little bit of acid is good, why not have a lot of acid? Well, the structure of aspirin also includes an ester, and we don't want to risk hydrolyzing that ester. We just want this to be acidic enough to make sure that our carboxylic acid is in its acid form, not its conjugate base carboxylate form. So let's go ahead and swirl this around, and we are going to add this to our water and acid. And here we go. We'll swirl this around a little bit. And if you notice, there's a problem. We don't have any precipitate. Well, we're going to need to let this cool down. So let's rinse this with water. Now I was so careful about not adding any more isopropanol than we needed. I'm not going to be careful with adding water. We're fine. We can use as much water as we want because aspirin has a low solubility in water. And it's nice not to have to worry about amounts. Just squirt to your heart's content. Okay. Fantastic. So this is now mostly a water solution. It contains some acid. It contains our material. Also contains some isopropanol. And that isopropanol doesn't help us one bit, but it's what we had to use for this extraction. So to help this along and to help get some precipitate, what we're going to do, and there may be just a hint of solid forming. Let me talk first. I'm not sure if you can see anything. It's hard to tell if those are gas bubbles. Those might be just slight air bubbles. Okay, so what we're going to do is we're going to put this on ice, and that will help our cause of getting our material to precipitate. So let's put this to the side. Let's get this ring stand out of the way. And here is just the classic lab tub of ice. And let's stick our flask in here. Great. Nice and cool. Okay, we'll leave that on ice for a little while, and hopefully we will see some precipitation occurring, and we'll get a nice yield of, or at least a reasonable yield of, our aspirin recovered from these tablets. Okay, we've been cooling now for a good half hour. And you can see there is solid, and that's not ice on the bottom, that is solid on the bottom. And that looks promising. I don't know if it's 100% of the way done, but we'll give it a few more minutes on your own while we do some other work, but that's good to see. Now you notice there's a second flask over here. So this is water with a little bit of sulfuric acid and our product. This is just water with a little bit of sulfuric acid, and I'm cooling that as well. So we're going to end up doing a filtration, and we want to make sure that everything we use is nice and cold. So I am pre-cooling some of our liquid to make sure that we can rinse it with cold liquid as well. So you don't want to use warm solvents when you took the time to cool something down. You don't want to just rinse it with some warm or room temperature solvent and risk dissolving more of your product right back into your rinse solvent. So this is going to keep cooling for a little bit, and now we need to get set up for our filtration, because I think we've seen, maybe not all the product we will, but the returns are diminishing as we wait longer. So let's go ahead and get the filtration set up. So great, here is our setup. Now, we want the solid, we don't want the liquid. So therefore, we're using a Buchner funnel, suction filtration. We have a sidearm Erlenmeyer flask. We have this connected to our house vacuum line. We have a Buchner funnel, and we have a filter paper in here. Now, our solution that we're filtering is essentially water. So we're going to use water to seat this filter paper and get it in place. So let's go ahead and squirt a little water in here and make sure that we're covering our holes, and we are. That looks good. Now, before you do a filtration, you want to turn on your suction and get that filter paper nice and sucked in to the filter plate of your funnel. And now we're going to filter our solution. Now notice I've left the solution, it's hard to see off camera here, but I've left the solution on the ice. Very often when students do filtrations, they say, oh, I'm done cooling this. And then they'll take it and they'll put it on the bench top and it'll start warming up. Well, what can happen as it warms up is you might start dissolving your material. So keep the flask on the ice. Don't put it on the bench top to let it warm up. You put it on the ice to keep it cold, and you want it to stay cold. So we're going to take this, give it a swirl to try to suspend that product. And now, bam, look, okay, that stuff's pulling through like crazy. Looking good. Let's swirl that a little bit more, get it nice and suspended. Notice this is a much faster filtration than what we saw with the isopropanol. We're filling up our funnel, so let's wait a second and let this draw through. Now, as we filter more and more, we get more product coating the filter paper. So the rate of filtration slows down because there's more resistance to the flow as we fill up with solid. That's a good sign. If there were no resistance, we might suspect that we don't have any solid to resist the flow. So this is fine that it's slowing down. That always happens. Oh, and I'm not actually seated very well either. So as this drips, we can take a little more. Now I say we want to keep it cool, and you could say, well, while you're filtering, it's kind of getting warmer too. Well, it is probably getting a little bit warmer, but that's a much smaller effect than taking your flask and just leaving it sit out on the bench top. We want to minimize the impact, but rarely will we do a perfect job of controlling temperature. We just need to make sure it's good enough. Okay, this is going to take a little bit of time, though it's running completely as we'd expect. Filtrations get slow. Now, if you find things that are really slow, let's say we're going to run this experiment again. You might say, wow, that filtration got kind of slow at the end. So maybe the answer is, for this amount of material, I'd be better off choosing a larger Buchner funnel. And that would give a larger surface area in the filter plate. And so we get less resistance from the solid, and the rate of filtration might be quicker. So there are, if you feel that things are getting too slow or a problem, you can always reconsider, were I to do this again, how might I change the experimental setup to avoid that kind of problem. This is not overly slow at all, although I'll admit, as I talk in the microphone, this feels like it's taking kind of forever. But in terms of lab time, this is actually, everything's flowing. It looks great. For the sake of the video, I'd like it to be a little faster. Okay, that's the last of that. We got a little ice in there. Not always the best thing. That is one problem when you cool things on ice and you pour it out. Sometimes the water from the ice bath will drip into your solution. Now, for us, the solution we're filtering is essentially ice. Who cares if we get a little water, or it's water? Who cares if we get a little ice water in there? But if we are filtering a solution of ether, we may really want to take better care and maybe dry off that flask before we turn it up virtually upside down to pour into the funnel. So again, we're dripping away. Now, what's going to happen when this finishes? Well, we do want to give this a little bit of a rinse. And so here is our solution. I'm going to put just a little, since this is slow, I won't do a ton of rinse. But we'll swirl around a little bit of that clean solution, that cold clean solution, into the flask. And now once this dripping stops, we'll just give it a little bit of a wash with this solution. We are almost done. You'll be able to just watch this dripping, and when that stops, we'll know we filtered everything through. And it is almost there. I can see from a little bit higher angle than the camera. Okay, that's kind of the end of it. There we go. Okay, that looks better. Now, let's give it a little bit of rinse. And that'll be the end of the filtration. So once this filtration is over, I'm going to let this stay on the funnel for a little bit. Let this, we'll pull air through our solid, hopefully let it air dry a little bit. It won't be complete. And once it's dry enough that I feel like it's going to be a free-flowing solid, I'll transfer it to a watch glass, a tiered watch glass, so we know the mass of that watch glass, and then we'll be able to determine the mass that we've added to it through the solid, and we'll be able to determine a yield. So you can see now it's splattering, so all the liquid is through, but we'll let that keep drawing air through the solid so that we continue to get some drying. Okay, so this is now, I don't think it's completely dry, but it's dry enough for us to transfer it onto a watch glass. And so I have a tare weight on this watch glass. It's like 31.50 grams. And let's gather our material. Pull out the adapter. Let's slide this to the side. Okay. And now we're going to, I don't know if you can see, there is solid in there, and it's pretty flaky. When I remove this solid, I'll remove the solid, and I'll probably bring the filter paper along with it. So that's just something to be mindful of. We will have to remove that filter paper. That looks beautiful. Scrape it around the edges. And once it's free, we can use the spatula. There, it pops right out. There we go. That's the back of the filter paper, and let's do our best to scrape these crystals out. Great. Not perfect, but you know, at some point you say, if I lose 5 milligrams, that is just not a significant amount of material. You're never going to be perfect. It just has to be good enough. So there's our product. You can see it's kind of, a lot of it's adhering to the other side of the filter paper. That's fine. We'll just let all that sit out and air dry. And once that's dry, I'll get that material off the filter paper and get a mass of just the watch glass and the solid, and that'll give us a mass of the product. Alright, so here we are. We have this solid. This is the final solid. This has been allowed to air dry, and the mass of this solid, not including the watch glass, is about 2.37 grams. Now 2.37 grams is not fantastic. I think the amount of aspirin in those 30 pills was just under 10 grams. So 2.37 out of 10, that's in the 20 to 25% recovery range. Not great, but still, this is now recovered aspirin. Well, now this is a really nice looking solid. It's nice, white, colorless solid, just like we'd expect pure aspirin to be, but we still need to gather NMR data, and we'll want to gather some melting point data on this compound. So anyway, initially it looks like about 20 to 25% yield, or 20 to 25% recovery. You know, we didn't actually make anything. All we did was recover material from the pills.
Okay, let's talk about our recovery, our percent recovery. We know that we used 30 pills. And these 30 pills had a total mass of 11.31 grams. Now, this is total mass. This is not the amount of aspirin. This is the amount of aspirin plus the other material in these pills. The actual amount of aspirin in these 30 pills was 325 milligrams times 30, because that's how much active ingredient we have in each pill. So we actually had 9.75 grams of aspirin. So this is our theoretical maximum, 9.75 grams. What did we get? Well, we got 2.37 grams. So this is our actual. Over here on the left is our theoretical. And if we divide actual by theoretical times 100, we come up with a whopping 24% recovery. Not a fantastic recovery. So, but hey, that's what we got. We can't say it should have been better, so we'll say it was better. That's what we obtained. So you might say, well, how could we have done better? Well, in precipitations, time is a big factor in a lot of precipitations. So maybe I could have taken that Erlenmeyer flask with the acidic water in it. I could have put it in the freezer overnight, and that would have given those crystals a longer time to grow. So maybe we just didn't give this enough time, and we could have improved our yield. And so that'd be something to try, to experiment, to improve the procedure. But anyway, we got a 24% yield, and we got really nice material. So now that we have this, let's go ahead and take a peek at the NMR spectrum and make sure that what we got was actually aspirin. So here is our full NMR spectrum, and we have a window running from around 16 ppm all the way down to -4 ppm. And you can see different peaks that show up in our spectrum. This, on first glance, I'll say that this looks like a fairly clean molecule, whatever we've isolated, and hopefully it is aspirin, because there's just not a whole lot of extra peaks down here in the baseline. So this looks good. I will highlight that down here around 13 ppm, this is our carboxylic acid. And now let's zoom in to the more interesting regions of the spectrum, namely the aromatic region and this region down more upfield. But let's look at the aromatic region first. So here is our aromatic region. This is the downfield region of the spectrum in the aromatic range of around 6.5, 7 to 8 or so ppm. So let's draw in our hydrogens on the aromatic ring, and you can see we've drawn in 4 of them, and on the spectrum we have 4 hydrogens showing up. Our 4 horsemen, they look great. We could try to assign these, and in fact I will. Let's label these around A, B, C, and D. The carbonyl is a nice strong electron withdrawing group, and so that is de-shielding for A. And note that A has one neighbor, that's B, and that's a doublet. So A should be a doublet, and it is. That's its multiplicity. The other doublet, therefore, would be D, which also has one neighbor. So that would assign us D. Now, if we drew multiple resonance forms, and I'm not going to on the screen, but actually C of B and C, both those have 2 neighbors. They both ought to be triplets. Based on drawing different resonance forms, we'd see that C should be the most D-shielded, and there's that triplet, and that would leave B to be the more upfield of those 2 signals. But those are 4 hydrogens. Note there's just noise in the spectrum. So this is a nice, clean looking sample. So now let's look at the more upfield region of this molecule. Here now is our more upfield region. We see 3 peaks on the screen. Only one of these corresponds to our structure. That's this CH3, and those 3 hydrogens, they have no neighbors, and they are a 3-hydrogen singlet. These other 2 peaks are residual peaks that show up from our solvent. So the solvent for the spectrum is D6-DMSO. DMSO has a signal of around 2.5 ppm, and the water signal, which we'll always see in our DMSO, shows up close to 3.5. So 2.5 and 3.5 are where we see these residual signals. So these peaks are definitely part of the spectrum, but they are not part of our molecule, so we will not interpret them, and that leaves 1 peak on this screen, that methyl group that shows up just a little bit past 2 ppm. So this spectrum looks good. This confirms the fact that the compound that we isolated from this from these aspirin pills is indeed aspirin, and it has a high purity. Now, it's not surprising it has a high purity because it came from a drug. Drugs have high purity compounds, but we don't seem to have a lot of other impurities, and of course nothing bad happened during our isolation process. We didn't destroy our ester or anything like that. So this is good looking stuff. For time purposes I won't throw in the melting point, but this stuff melts at about the literature value of aspirin, which is around 135 Celsius. So this is a successful isolation, not the greatest yield, 24%, but it did successfully afford us a pure sample of aspirin. I certainly hope you enjoyed this video. Please subscribe, like, or leave a comment. If you'd like to see some other experiments included in these videos, please let me know in the comments section. Handouts for the procedure of this experiment and the NMR spectra are available through links in the description. Thanks for watching, and take care.